Okay, so let's start. In the last lecture, what we have seen, okay, we have discussed the ideas of what relativity actually means, and we have discussed the postulates of the relativity. Okay, and let's try to understand this relativity of simultaneity. Let's look at the simultaneity in relativity. The simultaneousness of the events. Okay, so in Newtonian mechanics, what we know, so if we are having two events, let's say they are simultaneous in one frame of reference, okay, they are always simultaneous in the another frame of reference. That means it is due to the absoluteness of the time. Okay, so that what it means, suppose if you are having one frame of reference, one observer, he is having a clock, his clock, and another observer, he is having his own clock. Okay, so you can think as a universal clock for both the observers. They read as the same time. That's why these events appear to be simultaneous in both frames of reference. Okay, now let's look at the departure of this idea from the point of view of the relativity. It's actually the consequence of the finite speed of light. In Newtonian mechanics, the speed of light or the speed of any material particle, it can exceed to infinity. Okay, so there is no limit on the velocity. That's why events appear to be simultaneous. But relativity imposes a restriction on the velocity of the light, okay, or velocity of a signal in an inertial frame. Okay, the bound is given by the speed of the light. Okay, so it gives us actually a departure from the ideas of the simultaneity of the Newtonian relativity. So let's try to understand it in a more detail. Suppose if you are having, what it means, let's say you are having an observer, he is in the rail car, okay, and there is a clock attached with it. So think a rail car here, okay, which is moving with respect to some ground observer. Let's try to call this as an observer O prime, and you are having an observer O here, okay, and this observer O prime is moving with the velocity v. Clear? Okay, so now let's look at this very concept. Let's say an observer here in this rail car, okay, he is at, let's assume he is at the midpoint M, okay, and he sends the two flashes of light towards the ends of this very car. Let's say you are having a flash of light here, it reaches to this end, let's say end B, and it reaches to this very end and A. Okay, got it? So because the speed of light is finite, okay, speed of the signal is finite, it is c, so that means the amount of time it has taken from M to reaching to B is the same amount of time reaching here. So that means the events A and B are simultaneous for the observer O prime in his frame of reference. Okay, we call this frame of reference as a co-moving frame of reference. Okay, so think it as a clock, okay, and with the clock you are attaching a frame of reference. Okay, so that frame of reference I will call as a co-moving, and if this clock is moving with certain velocity with respect to an observer, I call this frame to be a co-moving frame. Got it? Okay, now let's look at the observer O. Okay, so when this moves with the velocity, let's say with the velocity v, what this observer, ground observer, observes. Okay, got it? So what he will observe, he will see this rail car, okay, rail car moving with certain velocity v, and he will see these ends, okay, like this. Okay, so that means these ends are so some distance vt. So it means this observer will observe this end has moved towards M, and this end has moved away from the M. Because of its velocity. Got it? Yes, so it means the observer, okay, for the observer O, the signal, okay, which M sends towards A will reach this end first, then the signal here. Clear? Because for this observer, this distance is longer than this very distance. So it means they will not appear simultaneous to an observer O. Okay, got it? So in other words, the events which were simultaneous in both frames of reference from the Newtonian perspective, they are not actually simultaneous from the Einstein theory of relativity. Okay, got it? So we call this as the relativity of simultaneity. Simultaneity is not an absolute concept, it's a relative concept. Clear? And let's try to construct how much amount of time, okay, okay, they disagree upon, so that there can be the simultaneity. Okay, or let's say how much, let's figure out the time difference, this much of time difference. Okay, let's say if this is T1 is the amount of time it takes from M to, let's say, A prime, and it takes to some B prime, T2. Okay, so let's figure out this amount of time difference. Okay, it will give us the non-simultaneity, this kind of time difference. Okay, let's see on what factors it depends on. Okay, how it varies with this velocity of light. Okay, and in the end, if I put velocity of light to infinity, the Newtonian limit, we should retain actually the notion of the simultaneity of the Newtonian mechanics. Clear? Got it? Okay, let's try to construct it. Everybody has got what I mean by it? Huh? Okay, so let's okay, do some mathematics from here. Suppose if you are having this observer, let me draw again this very car. Okay, so you are having point M, so you are having A here, and you are having point B. Okay, so let's assign time here. Some time T prime is equal to 0. So I am having in the O frame of reference, I will assign the coordinates to these events. M is an event, B is an event, A is an event. Clear? Let's assign coordinates to them. Okay, I will start at some T prime equal to 0. I initialize my clock at some time. Clear? And at that point of time, I send the signals towards the ends of the car. Clear? So much more. Let's assume L prime is the length of the car. Okay, so you are having L prime as the length of the car measured by the observer O prime. Okay, got it? And I will assume the coordinate here, it is some x naught at some position, because okay, you can start x naught to be 0, there is no problem, but for the sake of completeness I will assume some finite coordinate, but at t prime equal to 0. Now tell me how much distance this is. So this is actually L by 2, because this is the midpoint. This also, sorry, L prime by 2, this also what? L prime by 2. Now assign the coordinates to these points. This point A, think this here as a coordinate axis, x and y axis. You are having x, or x and t axis I should say, x, and this will be minus x. Now tell me what are the coordinates here. So let's write the x coordinate. What will be the x coordinate? So let me write the x prime. So how much is that? So that is simply x naught minus L by 2, and let me write it as t1 prime for the time being. Clear? So the time associated with this event is t1 prime. Okay, so on what are the coordinates for this point B? So x prime is equal to x naught plus L by 2, this much of distance, and let's write t2 prime. Okay, because in O prime, A and B are simultaneous, is it? Clear? So in its own frame of reference, they are what? Simultaneous. What does that mean? So it means T1 prime is same as T2 prime. Okay, because it will take the same amount of time to reach both ends. How much is that? Anybody? How much is that? L by 2 divided by C. So distance by velocity of light. So it is L by 2 C. So this is the amount of, okay, I will write L prime. So this is the amount of time it takes to reach from point M to point B, or point M to point A. They have to be same. Got it? Now let's go to the, okay, so this is for observer O prime. Let's go to observer O. Okay. So now let's assign the coordinates for the observer O. Okay, for the observer O, first let's say for the observer O, let L be the length. Okay, L be the length of the car. Okay, I will use L and L prime different. So an observer, okay, the O prime observer will measure his length to be L prime, but O will measure its length to be what? L. Okay, we will use these L and L prime to be different for the time being. Clear? Okay. So now let's assign the coordinates to these points A prime, okay, and B prime. Okay. So let's assign from the perspective of O. So if I assign the coordinates from the perspective of what? O, then I will be able to relate the events from O prime, okay, the events from the perspective of O prime with the events from the perspective of O. Is it? So I can figure out a relation between the two. Got it? Any problem? Huh? Any problem? No problem? Okay, now tell me, okay, in this O prime, okay, how much is the amount of time that it takes the signal to reach A prime from M? Okay, how much is the amount? Okay, tell me amount of time required for a signal to take from M to A prime. Okay, A prime is the event observed by which? O. Okay, and B prime is an event observed by O. Clear? I want to figure out what is the amount of time it takes from where? M to A prime. How much is that? Now look here, this A prime has actually moved towards, let's say, right. How much? By V of T1. Clear? And this B prime has moved towards the right by time T2. Okay, by the distance. Let's say this is some distance Vt2 and this is distance Vt1. V is the relative velocity. Clear? Now tell me how much is the time it takes. Let's write T1. How much is the time it takes from, okay, T1 is the time taken by signal to reach A prime from M. Clear? How much is that? It's L by 2, yes? Okay. Minus Vt1 divided by C. Okay, now tell me what is the, okay, T1, okay, also let's write T2. How much is that? L by 2 plus Vt2 divided by C. Now let's solve for T1 and T2. Clear? So we can write then this T1 into 1 plus V by C, that's equal to L by 2. So what it gives me? T1 is equal to L by 2 to 1 divided by 1. Similarly, I can get also T2 I can get. You take the other T2 on this side if you okay. So T2 is 1 divided by 1. So what you get? So therefore the amount of time difference. I need to calculate this time difference. Clear? If this time difference turns out to be 0, that means it takes the same time to reach the both ends. Clear? If it's non-zero, then it does not take the same amount of time. It means they are non-simultaneous. Okay? So how much is that? L by 2 into 1 minus V by C minus 1 divided by. So how much is that? So L. So you are having so LV by C square. So there should be some C, factor of C we forgot. So there is a 2C. Okay, so it will be C square 1 divided by 1 minus V square by C square. Okay, or in other words, I can write this delta T, amount of non-synchronicity or the amount of non-simultaneity, it's equal to L V by C square into gamma. Gamma is equal to gamma square. Okay. So this is very important formula. Samajh? So it represents the amount of non-simultaneity of the events. Clear? Okay, now let's look at the Newtonian limit of this thing. Okay, so let's look at Newtonian limit. So in the Newtonian limit, this velocity goes to what? Infinity, because there is no bound on velocity. Clear? Or in other words, v by c is very small. V by c is very less than 1. Tell me what will happen this delta t? Then delta t tends to 0. Or in other words, t1 is same as t2. So it means it takes the same time to reach both ends even from the observer O. Got it? So in other words, in the Newtonian mechanics, you are having a universal clock and all inertial frames read the same time. Got it? And that is why you are having simultaneous events in the Newtonian mechanics, not in the Einsteinian perspective. Got it? Any question? If you have any question, just tell me. Okay. Now from this example, what we have arrived at, there is an important conclusion. The way we think of time, or in other words, the way we think of assigning time to a moving clock with respect to a stationary observer. Got it? So, or the way we assign coordinates to a given point. Samajh? Got it? Okay. Clear? So, it gives us actually a drastic departure from the Newtonian mechanics. And this provides us actually an understanding how you can relate time or the clocks for the two observers. Okay, so this gives us the concept of what we call as a time dilation. And you can actually produce the length contraction as well from the same idea. Okay, because we have used different lengths from the two frames of reference. Okay, L and L prime we have used completely different. Okay, so you can figure out the relation between the two as well, and it is actually the consequence of the second postulate of the relativity. Okay, now let's look at the consequence of this principle, the relativity of simultaneity, on the measurement of the time. Okay, now how we define a clock? An easy way to understand is that if a clock ticks, let's say you are having a clock, if it ticks, that means you read a time. Clear? Every tick gives you a time. Clear? Okay, so let's think of a clock. Okay, so in a frame of reference, let's think some clock. Okay, in certain frame of reference. Okay, call that as an O prime. It is at rest in the O prime. Got it? And I will call this O prime as a co-moving frame for the clock. Let's say this very clock. Okay? And this frame is moving, or in other words, this clock is moving with respect to another observer. Let's say that is O. Okay? It also contains its own clock. Clear? And I have nothing to do with this clock. And I have to only measure what is the time that you can measure from this moving clock. Okay, got it? Okay, so in its own frame of reference, this clock is at rest, is it? So think of a clock. Let's say I am moving with me. I am having a clock, and that's rest with me. Clear? So if what will be the coordinates? So I can say, since there is no coordinate displacement, this delta x is 0. Clear? Or in other words, you can say x. I can assign this coordinate to be 0. Got it? And let's call the time it reads, that is delta t prime. Okay? So this is one tick. You can say delta t prime as one tick. Clear? Okay? So in this very frame of reference, you are having delta t, what you measure, or in other words, you can say the coordinate time. So in another frame of reference, you think this as a coordinate time. Okay, delta t, this is the amount of time that is measured by us with respect to this very clock. Or in other words, I am measuring the time of this very clock. Clear? So of this very moving clock. Okay. So there is a relation, well-known relation between the two. So this delta t is actually equal to gamma times delta t prime. And so we'll give an argument for this, how to prove it. Okay. So it says what? This delta t is larger than delta t prime, since this gamma is what? Greater than It is greater than 1 actually for finite velocity. Okay, so we call this delta t prime as a proper time. Okay, and we call this delta t as the coordinate time. So in other words, from this very relation, you see that the moving clock slows down. Huh? Okay, so if you are having a clock that's moving with respect to an observer O, let's say with respect to another observer, you will always see this moving clock is slowing down. Huh? Got it? So is it okay from this very formula? So we call this as a time dilation. Huh? And let's think of a clock. Okay, we call this as an O prime frame of reference. Okay, so I'm considering as a pulse clock. So there is a light pulse. So think the distance is d. Okay, between these two mirrors. These are two mirrors, and I am sending a signal from here to here, and from here to here. So I can say one tick. Okay, is that the if you send a signal from here to here, you measure one tick. Okay. And the another tick, you can say the signal comes back. So this is my clock. Clock is simply the ticking. Clear? Got it? Okay, so in this frame of reference, you can measure, let's say, the time. What will be the time? Okay, of a one tick. That will be simply d by c. Okay? Any problem? So this is a clock attached to a moving frame of reference. Now, let's say this clock is moving. Huh? An observer who is sitting, let's say you are having an observer here, and we call this as an O. This clock is moving, let's say, in this very direction. Huh? So what observer will see? So you are having, let's say, the signal which you send from here, because it is moving. Clear? So you try to send it this way. Okay, although for him it's going it this way, but the observer will see what? As the clock is moving, he will see this flash of light going here. Okay, so this is your mirror, like this. I will take only the three events. Then he will see the signal hitting this very thing, because this has moved a distance. That's why, since for this observer, this is moving a distance of this thing, and in the meantime, once you send a signal from here, in the meantime, this end has reached here. That's why it goes this way. Clear? And similarly, since it's moving, it will move a distance. In the meantime, this mirror has come here. So, okay, so let's say it covers a distance d. Okay, this diagonal distance. This is already your d. Clear? So how much is the distance covered? How much is the distance covered? No, it is the moving frame. It is v t. Clear? Or v delta t. I have tried. V is the relative velocity. Everybody got it? Okay. So now tell me by formula. So what I have to do? I have to. Okay. So let's calculate the time in this very frame of reference. Oh. So let's calculate the amount of time it takes the signal to reach from this point to this point. Let's say some point A to some point B. Got it? So let's try to figure out. So that will be actually d by c. Clear? Okay, so what is d? Now tell me what is d. Use the Pythagoras theorem. So it is root of d square plus v square delta t square divided by c. Got it? Huh? So now let's calculate delta t. Delta t comes from here as well. So it will be something 1 minus v square by c square into delta t square, that's equal to d square by c square. Now tell me what is d square by c square? It is delta t prime square. Okay, so in other words, or this delta t is equal to, okay, 1 by root of, so that's actually gamma, gamma delta t. Okay? So you can do the analysis other way around as well. So you will figure out delta t prime as gamma times delta t. You can think, okay, this as such, and this observer is moving. Clear? As the reverse effect, you will get the same formula. Okay, with delta t and delta t prime interchanged. In that case, if you do, okay, here the delta t prime will be is the proper time. In the other case, if you do it in the reverse way, so then delta t will be the proper time of the clock. Clear? समझ आया? Okay. So if you have any more questions on this thing, so okay. You have written it? Huh? Okay, so now let's move ahead. So let's write an interval, huh? Space-time interval. Okay. So let's think of two events which are infinitesimally close to each other. Let's think of two events P and Q. Okay, which are very close to each other. Let's say the coordinate here is xi and this is xi plus dxi. Okay, so this is simply a label. Huh? Okay, I means this is the ith coordinate. I will do the analysis in detail in the next coming lectures. Okay, for the time being, I am considering two events at xi. Xi means it is the okay. So let me write this. Xi means some ct x y z, and this means c d plus c delta t dt, and x plus dx, y plus dy, z plus dz. Okay. Now then I can define the interval, which is very important quantity. Okay. So I can define an interval between these two events. Interval means simply the length between the two events. Clear? So interval between P and Q. So like this, ds square is equal to minus c square dt square plus dx square plus dy square dz square. Actually, in field theory, we have done the interval minus here, minus here, minus here, and plus here. Huh? But in general relativity, we are doing a different kind of convention. Forget. Okay, we are using this kind of definition for the interval. Okay, interval you can think, let's say, as the length between the two events. Okay, or the distance or the length of the distance between the two events, because we are in the four-dimensional space-time here. I am doing all the Minkowski space. Huh? Okay, we are doing only the special theory of relativity. That means we are in the flat space-time. Huh? Okay, so the distance between the two points will be in terms of the Euclidean case. If I am having the distance between 2 points x, y, z, and let's say x prime, y prime, z prime, you simply do what? Squares of the difference between the 2 points. Huh? Okay, let's say r. Okay, so x square plus y square plus z square. Okay, so that is the distance between the 2 points. Huh? Okay, the Euclidean way. But since we are in actually the non-Euclidean geometry, or the Minkowski, I should say the Minkowski geometry, okay, where we define the length between the 2 points, two events P and Q as this way. Okay, there is a sign change here. Clear? And this length we call as an interval. Huh? Okay. Now there is a very important. Okay, the consequence of this thing, speed of light, constancy of the speed of light. Okay. We will define these later on, but we are just looking at what are the consequences of the postulates of the relativity. Okay, particularly the second postulate. Okay, let's say in one frame of reference. Okay, let's assume in one frame of reference, call that as O prime. This ds prime is equal to 0, or let's say O. This ds is equal to. That means length between the intervals is what? 0. Got it? Now let's look at this very formula. So if I am looking at this very formula, if this becomes 0, so it means these 2 points P and Q must be connected with the velocity of light. Otherwise, it will not be 0. So you can see. So if this becomes 0, you take it on this side. What do you get? C square dt square is like this thing. And divide by dt square, you will be having c square is equal to this object divided by dt square. So that is actually velocity square. That will give simply the velocity between what? 2 points P and Q are the events P and Q. So how much is that equal to? Okay, so let me write it this way. In this case, what you'll get? You get simply c square dt square equal to dx square plus dy square plus dz square. Okay, so it implies this of, okay, so now divide by dt square, so you'll get like this. So or in other words, the velocity becomes what? Same as velocity of light. It means the two events are connected by the velocity of light. Okay. Now, since velocity of light is constant in all inertial frames of reference, got it? So if I take the another frame of reference, okay, since c is constant by second postulate, so it means what? It means in frame O prime, another frame which is moving at a relative velocity, let's say v with respect to the O. So it means in this O prime, this ds prime is also 0. Got it? Samajh aa? Okay, so what it means? So if you have the interval vanishing in one frame of reference, it's vanishing in the another frame of reference. Got it? That means the value of the interval is same in the both the frames of reference. Got it? Okay. So this is one of the conditions which will be useful. But we are going to figure out. So there is a general relation between the two. The intervals defined in the two frames of reference. That's like this thing. So ds is equal to, or in other words, ds square is like this. Okay. So the interval is an invariant quantity. So we are trying to prove this very condition. So samajh aa? Based on this kind of observation, that means if an interval vanishes in one frame of reference, it vanishes in the another frame of reference. From this very condition, we are trying to figure out a more general kind of condition in which this object remains invariant. Okay? Samajh aa? Okay. So it is all because of the constancy of the speed of light. Or if, let's say, if we have now proved this is invariant, that means it is same in all inertial frames of reference. Okay? So what does that mean? So then it represents actually the constancy of the velocity of light. In other words, defining the interval in this way means velocity of light is constant. Samajh? Because we have assumed velocity what? Constant. So samajh aa? A fixed value in the inertial frames of reference. Clear? Okay. So now, okay. So let's say I want to try to figure out the relation between the two. Okay. Since now we know if I am having one frame of reference and another frame of reference, you want to look at each other. So it means there must exist a relation between the two. Clear? So in other words, I can say, let's assume this ds, if it is defined in one frame of reference, so it must be actually proportional to ds prime. So samajh aa? Or in other words, I can say this ds is actually the function of ds prime. If I make a coordinate transformation. So samajh aa? So if I make a coordinate transformation from one frame of reference to the another frame of reference, then I should, okay, in one frame I will get ds, it should be related to what? ds prime. In other words, I can say ds is what? Function of ds prime. Okay, so let's make a Taylor series extension of this objective. Samajh aa? Let's do it. So a Taylor series expansion would be, what is the first term always? That's a constant term. So let's write that as a constant k. And what will be the another term? Okay, a derivative term multiplied by this value. Huh? So I will call that as some a, okay, multiplied by ds prime plus dz, all higher order terms. Okay? Got it? Samajh aa? So it is by Taylor series extension. By Taylor series extension. Okay? So you can ignore all higher order terms because it's an infinitesimal quantity. Okay? If this is an infinitesimal quantity, the all higher order terms vanishes or they are negligible. Okay, so now let's look at that kind of observation. If you are having ds equal to 0 in one frame of reference, it will be 0 in the another frame of reference. Okay? Let's figure out this very constant k. Now if ds is equal to 0, what it means? ds prime is also 0. Okay? So what does it mean? This k must be 0. Okay, so I will write by above observation. By above observation. Above means that. Okay, so that observation. So let me write. If ds is equal to 0, implies ds prime is equal to 0. So what it gives me? This k is equal to. So what it means though? Okay. So you are having this ds simply equal to, let me write, this a must be actually the function of the velocity. समझ आया? Because what is connecting between the two frames of reference? It is the relative velocity. So this a must become as what? Function of velocity. Let's say it is the function of some velocity. ds prime, and I don't know. It is a velocity vector. Clear? समझ आया? So let's call this as a velocity vector. Clear? समझ आया? Okay, now let's try to figure out whether this a really depends on this velocity vector or not. Now we are having a concept of homogeneity of space and time. Clear? When you are having homogeneity of space and time, what does that mean? Okay, so let's think of the isotropy first. So if I am having isotropy, what does that mean? My space is equivalent in all directions. When I am having homogeneity of space and time, it means my space is translationally invariant. It means it is invariant, I mean the same in all, okay, let's say in the translation. Clear? So when I think one frame of reference moving with respect to the another frame, okay? So if I am considering the inertial frames of reference, then both the frames are equivalent. Clear? So this object is defined for an inertial frame of reference. This is also defined for inertial frame of reference here. Okay. Now this a depends on the velocity vector. But if I assume isotropy and the homogeneity of space and time, okay, even if this depends on the, let's assume if this depends on the velocity vector, that means different inertial frames are more peculiar than the others. That means you are having a preference of the inertial frames of reference. You can distinguish between the inertial frames of reference. So if if my homogeneity of space and, okay, let's say if there is no homogeneity of space and time, clear? So it means if I make a translational invariant, the frame which is moving, it will be more preferred than the other frame, or the initial frame will be the more preferred than the other frame, because you can distinguish between the two frames of reference based on what? They are distinct in a sense. I am saying, I mean, we see the space and time are not homogeneous. Clear? Now if my space and time are homogeneous, it means both inertial frames are what? By definition, inertial frames are identical. Clear? But if I am imposing the condition this homogeneity of space is not there. So because of that very principle, I may be able to actually distinguish between the frames of reference. Got it? Okay. So in that case, this should not depend on what? Velocity vector itself. It should depend only on the magnitude of the velocity, because only the magnitude of the velocity is an invariant quantity. It does not depend upon the choice of the frame, because the magnitude does not depend on the choice of frame simply. Clear? So I can say this should depend on what? By homogeneity, this should depend on the magnitude. So this I will write simply A of E. Clear? Now let's try to figure out what is the value of this A. Okay? Let's try to figure it out. Let's assume. So everybody got it why it should depend only on the magnitude? Okay, good. Okay, so let's consider three frames of reference. K, K1 and K2. Let's say K1 is moving with respect to K as with the velocity. Let's say K1 is moving with velocity V1 with respect to K. Okay? And K2 is moving with velocity V2 with respect. I am considering how many frames? 3 frames with respect to K. And there is a relative velocity. K1 is moving with respect to K2 with velocity, let's say V1. Got it? So by using this very relation, now let's say in K1 frame, I will be having ds1. Got it? I should have put actually square. instead of this, I should have put a square, right? Square would be more good. So I will be having ds1 as an interval with respect to what? K. Clear? समझ में? Here I will be having ds2, okay, ds1 square. Okay, I will be also having what? Some element with respect to the 2. Clear? So now let's write using this very form. I can write this ds1 square as a of v1, let's say ds square. Clear? ds is the element of, for the k. Clear? Similarly, I can write this ds2 square as a of v2 ds square with respect to this thing. Now I can have this ds1 square as a of v12 ds2 square. v12 is the velocity between k1 and k2. Clear? Everybody is following it? Okay. Now let's use, you can write ds2, okay, ds1 and ds2. Let's write, what is ds1? So you write this as av1 ds square is equal to av2, okay, so then av1 to av of 2 ds square. Clear? So using first and second in the third. Clear? So or you get like this, a of v1 divided by a of v2 is equal to a of v1. Clear? Okay, now look at v1 is the magnitude of the velocity v1. v2 is the magnitude of the velocity v2. Clear? So does these magnitudes depend on the angle? No. So left hand side does not depend on the angle between the velocity v1 and v2 because they are separately the magnitudes. Now here v12 is actually the magnitude of the velocity, that is the relative velocity between k1 and k2, and I don't know at what angle they are moving. So they can be moving in the same direction, they can be moving at any angle. Clear? So in other words, the magnitude on the left hand side, right hand side depends on the angle as well. But the magnitude on the left hand side does not depend on what? Angle. Clear? So when it is then possible? It's possible only when, okay, so for this relation to be satisfied, this a must be a constant. Then and only then you have independence from the what? The angles. Look here, this gives you the dependence of the angle, but on the left hand side you don't have the dependence on the angle. Clear? So if this relation has to be true or this equation has to be true, this is only possible if a is a constant function. Got it? So if a is a constant function, ratio of two constant functions is a constant, and the right hand side is you are having also what? A constant. Clear? So this is satisfied only why? Satisfied only if a is constant. So now a is a constant. Clear? So that means I am having this ds square is equal to some constant a ds prime square. We can show that this constant is equal to 1. So this will be actually the assignment. Show that a is equal to 1. So it is ds square is equal to. So this is a more general condition. If you are not able to do, look at the electrodynamics notes. What we have done in the electrodynamics, there we have done actually special theory of relativity, is it? So this kind of principle I have already told you there. समझ आया? It's simply the recap of what we have done in the earlier classes. Okay.